Landeslager.
¿Ese no te preocupes?
stanno bene.
Dear colleagues, we are late because people are standing in line in the street. However, please find a seat. We are going to start very soon.
So we did fight and got a microphone.
Oh, one. What is that?
You can get as many microphones as you want down there.
Beautiful. Oh, and why do you have a microphone?
Normally you wouldn't. Normally you did the person behind the lectern.
No, I ordered one.
Ah,
Hello? Hello? Okay. Good morning, ladies and gentlemen. I welcome you to this important milestone event, the kickoff of the Quantum Flagship. My name is Marcus Wilkins. You probably don't know me. I'm coming from the Association of Engineers in Germany, and we will be the coordinator of the next coordination and support action for the Quantum Flagship, so taking it over from Tommaso, the QSA. And as we are already a little bit late, I would like to call on stage Professor Mlynek, and after him we have Gustav Kalbe and Tommaso Calarco in order to give some introductory notes how we came here and how the Quantum Flagship was established. So Professor Mlynek, please come on stage.
So, good morning, everybody. Isn't this a wonderful location? This is Austria at its best. Thank you very much, Austria, to welcome us today. Let's give them an applause. You are all experts, and my duty this morning is, in a very brief way, introduce somehow the flagship to you, especially the history. Now, we all know quantum science for over 100 years. And I just displayed this transparency with the saying of Einstein, because still, if you're working on quantum science in the lab daily, I wouldn't say you are irritated, but many things that you observe are still counterintuitive. And I don't know how long it will take until quantum science is considered as normal as classical science. So, what is so special about the second quantum revolution? Now, this is a reminiscence again to our Austrian colleagues. I think some years ago, the Dalai Lama was visiting Innsbruck. And where's Anton Zeilinger? I saw him. Where is he? Anton. He wanted to talk to you about the philosophy of quantum science, but he also knew there were experiments going on by Rainer Blatt, you know, these single ions in a trap. And what Dalai Lama wanted to see is the light of a single emitted by a single ion, the photons impinging on his retina. And this is what the second quantum revolution is all about. It's the production, it's the manipulation, it's the detection of single quantum entities. And its use, together with the superposition principle and entanglement in developing quantum technologies. Now, some people say there is a hype. Maybe that's true. This is the so-called Gartner's hype cycle for emerging technologies. And as you can see, you start with the innovation trigger, then you have the peak of inflated expectations. Maybe we are there right now. Then there is the valley of, you know, disillusionment, the slope of enlightenment, and then the plateau of productivity. So also quantum technology will have to go through this curve. That's quite normal. And we all know reality in the lab, and that's what I already said, looks different. That's a Dilbert comic, how's your quantum computer prototype coming along? Great. The project exists in a simultaneous state of being both totally successful, not even started. Can I observe it? That's a tricky question. So that's, let's say, the challenge. Now, how does quantum technology doing worldwide? Where are the main actors? And as you can see, Europe is doing well. This is from 2015. The numbers have increased in the meantime. So we have Europe, That's the annual budget in whatever, euros or dollars. You see the United States going strong, also Canada. You always have at the end to normalize to the population of a country. We have China. China is a real powerhouse. I recently was there. They are starting in Beijing, the Beida and Tsinghua University and Academy for Quantum Science with an annual running budget of 30 million euros just financed by the city of Beijing. I met a representative and I was asking him, how come? Is the city rich? And he said, we are not rich, but there's always money for science. This is Beijing. And I always repeat this to our politicians from Germany, and there is money in Germany too, as we will hear later on. There is Japan, and then also Australia. Compared to the size of the country, Australia is also going strong in that domain. Now, 2016 was important in terms of preparation of the flagship because scientists from all over Europe came together and wrote down what they called Quantum Manifesto. It was a white paper to really attract the attention of politicians also at the European level to quantum technologies. And again, you see here the participating scientists, how they are distributed among Europe, and it somehow reflects the R&D strengths of the main actors also in the European Union. So this is the Quantum Manifesto and its main messages. Communication is important, simulation, sensors, and quantum computing. And you won't believe it, Brussels was listening and they decided, well, maybe it's a good idea to have a new flagship besides graphene and human brain on quantum technology. So the European Commission announced the Quantum Technology Flagship Initiative in April 2016. This was a very wise decision. A high-level steering committee was established. I had the pleasure to chair it. And here are the institutions and also the companies represented in this high-level steering committee. And this is somehow representative for the idea of the quantum flagship. The quantum flagship, and I repeat this whenever I speak on it, it's not on basic science. It's on technologies. And the idea of the quantum flagship from the very beginning was to team up between academia on one hand and the private sector, companies, industry on the other hand, because the goal is at the end to contribute also to wealth creation, jobs, and so on in Europe. So as you can see, with respect to the companies, there are big companies, there are small and medium-sized companies, and there are startups representing really the landscape of companies somehow interested or already active in the area of quantum technology. Again, the main messages of the report, no surprise. They somehow followed also the Quantum Manifesto. There are 4 pillars: communication, computation, simulation, sensing, metrology, cross-cutting activities, engineering control, software theory, education, training. And then underlying basic science, but basic science in that sense that here projects will be supported that do not somehow naturally fit into one of the pillars. It can always be that there is a discovery or whatever that really sheds completely new light on one of these pillars, and this, of course, must be allowed to, is essential too for this flagship. Education training, by the way, very important. I was recently at the ETH in Zurich and learned that they will start a new curriculum on quantum engineering next year, where really engineers and physicists come together and offer at the master level a course. And I think we need more of these examples all over Europe to train our next generation in this overlapping area on engineering on one hand and physics on the other hand. There are ambitious long-term goals. I don't want to go through them. The challenge of the flagship is you have to be ambitious because otherwise there will be no enthusiasm. But on the other hand, you can't oversell it because if you oversell it and if you don't deliver at the end, that's no good for the science community, that's no good for the private sector. So the challenge really is, and we will discuss this today and tomorrow, I think, to have the right balance between ambitious but realistic goals, midterm, long-term, and not overdoing it. Okay, there is, of course, the governance issue. There will be a ramp-up phase. Thomas Gordas, I think, will say more about it. As natural, there is a tension between, how can I say, the community, the scientific community in its broad sense, and then, I wouldn't say the member states, but let's say Brussels. The quantum community has the feeling we understand what is going on, we should determine, and Brussels says we give the money together with the member states, we have to determine what is going on. Again, you have to find the right balance between these different interests, and I think we came up from the, as you will see, from the steering committee, high-level steering committee, with a governance structure that should work. Maybe we have to change it over the years, but we will see. Timeline of the quantum technology flagship. We are now here, kickoff. We have the ramp-up phase. There were 141 proposals. Maybe we hear more about it. 20 accepted. Many were in the area of basic science, by the way. There were overproportional many projects being submitted for basic science. But again, the idea from the very beginning was that mainly consortia from academia and the private sector on the four main pillars, communication, sensing, computing, and simulation should be supported. After the 3 years, we will see how it goes on. I think everybody wishes that there will be a continuation at a higher level, hopefully even of financing. We always talk about this 1 billion euros. But as you know, only half of the money comes from the European Union. The other half has to come from the member states. And as you probably also know, depending on which member state you are representing, where you come from, some member states are willing to do more than others. And again, we will hear more about it this afternoon. But I can only encourage those who are still working on your politicians in the various countries, go for it, convince them that it's a real good investment in quantum technology also from the national activities. Fine. So here we are. It's a great day. As I said, wonderful surroundings. We celebrate the kickoff after many years of, heavy, painful, sometimes discussions. And what I can only say at the end is this community that is gathering today did an outstanding job. Congratulations. You really went for something at the European level. I think we have to strengthen Europe. And one way to do this is through science. This is really, combining interest of different countries, even if there are also controversies. But science is really the tie between our European states. And I think this flagship can contribute to make Europe stronger. So again, congratulations to all of you. And I see Thomas Gordas and Gustav Kalbe sitting in the front row. Thomas, Gustav, also a big thanks to you as representatives from the European Union. You made this possible together with your directorate. Thank you very much, and I think this also deserves an applause. Thank you very much. This also makes it more difficult for Thomas and Kalbe, you know, to come up with new things. So, enjoy the day. Thank you.
Okay, thank you very much, Professor Mlynek. So the European Commission has already gotten applause, and I would now call Gustav Kalbe on stage to give a more detailed information on the ramp-up phase of the quantum flagship from the European Commission point of view and its governance. So please, Gustav, join me.
Good morning. It's for me a real pleasure to be standing here today at such an historical moment. And personally, I'm really proud that after so many years, we're now in a state of moving into a new area in quantum technologies. You have listened to the previous speaker, Professor Mlynek, who was very courageously and very efficiently leading the high-level expert group that, with its recommendations, enabled us to really now start the actions of the flagship. So when I said that I feel personally very proud to be standing here, I show you out of our archives the very first launch event we had on a European program on quantum technologies almost 20 years ago, day by day, where Professor Zeilinger just a few years before had shown that teleportation in practice can be done. We had a huge number of projects which were highly scientific, highly speculative, and now we are really here to move into the next stage. Now, why are we now changing the approach to supporting quantum in the Union? First of all, we have now reached a level where the field is mature. There are still many scientific challenges to be solved, but we have reached a maturity where we now can really think of exploiting it and giving the taxpayers some return on investment on the huge amounts that have been invested in the Union and across the countries. We also see that the first commercial projects and companies are appearing, even if it's still a small number, but year by year we see more and more coming out of there. We're also quite happily surprised that, as a difference to the past, we have regained industrial interest. It's no longer industrial players following it by the sidelines saying something might come out one day for us. They're now really actively engaging. Of course, you can imagine the traditional big IT companies, but we see more and more non-traditional players, particularly in the field of users, logistic companies, pharmaceuticals, aerospace, engineering, and so on, that are now massively investing there. And then, of course, as Professor Mlynek showed in his previous slide, there are huge efforts and investments also going on in the rest of the world. And as here the markets are not established yet, we have still the opportunity to take advantage of the scientific excellence we have here in Europe to establish the markets and develop an industry that is genuine in Europe and not depending on imports from other regions. So all of this motivated the Commission to launch the idea of a flagship in the quantum technologies. So here I just want to briefly summarize what is the whole idea behind the flagship. So it very well resumed in the first sentence. We're bringing together an ambitious research agenda, highly risky topics with a long-term vision in a field where there is a prospect of return on investment, but where we need to coordinate national investments, with Europeans, coordinate the different research agendas. We are facing a challenge, an endeavor that a single player alone will have difficulties in succeeding. And then, of course, we have to put in place a governance to ensure that we optimize our efforts and pull all in the same direction and don't lose our efforts. So the political mandate, as was already mentioned before, in 2016 we had Commission communication putting the ambition, which was very soon after endorsed by Council, and I think it was a unanimous support by the member states that were really pushing, saying there's a clear added value, there's a real motivation of having a coordinated European effort in this area, and the Commission should go ahead and launch a Flagship. Now, more detail about the quantum technologies Flagship. It's not, as the quantum program in the past, based only on scientific excellence. Here, the core idea is really to take the scientific results that we have in the universities, in the labs, and bring them to fruition, create value, create products out of them, commercial applications, and build an industry around it. We want to really focus on the innovation more than on the science, although the scientific basic stays an important aspect that is and will continue to be supported in the program. From the very beginning, even if this was a game changer, we insisted that this should be driven by the needs of the users, the needs of the suppliers, to have really this engagement of the industrial players, to have the market pull, and have the technology supply from the scientists. And we were very happily surprised when we saw the outcome of the first call for the ramp-up phase, where we had over a third of participants coming from industry with a real participation, and 1/3 of those were SMEs, which if you look across the different programs we're funding, it's quite an achievement. Then finally, let's not forget that this area of quantum technologies is highly competitive, and we want to have an instrument that allows us to keep the excellence in Europe, to have the most brilliant scientists and more innovative spirits working for the benefit of Europe, and create the value here in Europe and not in other regions. So this, you have seen the slide before, just to situate where we are. Indeed, we're now in the ramp-up phase of the Flagship, but let's not forget that we have already running the Quanta project, which is bringing together 34 funding agencies across Europe working on this topic. And this is complemented, of course, with a more mature pilot, which we are now having open, where the call will close at the end of the year, which is looking at the more advanced, really the field trial aspects, where later on we hope that the results of the Flagship will feed in. So briefly, we had the call closed this year. The projects have started now on 1st October, so it's a very timely event we're having today. We had 130 million euros assigned to that call, plus some additional money for the coordination, which will help us in the governance of the Flagship. The QKD testbed will close later this year, but complements very nicely what we're doing in the Flagship. And then let's not forget that there are other programs that have a component of quantum that are supported by the Union. Just to draw your attention to the space program, where we have now quite a good collaboration. We see there's high interest from the various space agencies, including Galileo, to include quantum components in their satellites and build a network. And for us, it's to see how we can connect this with our initiatives. Professor Mlynek showed you the logic or the areas that the community at large found the most advantageous, the most promising, with the highest return on investment to support. So the Commission, when it published the work program, of course, was following quite closely those recommendations. And therefore, it's no surprise that we have those 4 application areas that were the main focus of the call: in computing, simulation, communication, and metrology. And all this underpinned by fundamental science to fill the gaps and have the possibility to identify new promising areas that later on could go into the application areas. So now this is the outcome of the call. I'm showing you here the number of projects that were retained and funded per area, together with the respective budgets. So at first sight, we could say it's a reasonable, fair distribution of the topics. On purpose, we didn't assign dedicated budgets per area, with the exception of the fundamental science. The only thing we said is we want at least to have 2 major projects in each of the application areas. But other than that, we want to have a certain competition to see what is the maturity, what is the center of gravity, what is the interest of the community. Now, when you look at the fundamental science, we were happily surprised to see that a number of them are really cross-cutting, addressing more than just one application area, and in case they succeed, would have a huge impact on the other areas. The only area we're a bit worried that we don't invest enough is quantum computing. That's why we are now thinking aloud of launching an additional call in 2020 on quantum computing, but they're based on semiconductor approach, on quantum computing approaches that are compatible with the microelectronics manufacturing process to have another technology platform that is scalable and compatible with existing industrial processes. Now let me move into the governance. What you see here is a very simple picture showing the main actors. This clearly and closely follows the recommendation of the high-level expert group. So you have on the left side the quantum community at large, participating, not participating in a European national program, doesn't matter. These are all the actors, all the interested parties. They have set up a quantum community network where each country has a lead delegate to act as intermediary between the national communities and the flagship governance. In the middle, of course, we have the decision-making bodies where on top we have the Board of Funders and the Commission, where you find representatives of the different funding agencies. That's where the strategic discussions are going on, where the orientations are being discussed, where we take stock of how do we evolve, how do we progress compared to our objectives, and are some corrective measures needed. Now this is helped by a strategic advisory board where we will bring together a number of high-level, highly reputable experts from science, from industry, from RTOs to provide input on any matter of importance for the decision-making at the political level, research agendas, recommendations on the governance, future orientations, monitoring of the activities, etc. This follows closely the previous experts group we have in the mandate. There's no major surprise there. And then, of course, we have the performers, the projects that are implementing the work of the flagship, be it the quantum flagship projects themselves, be it the Quanta projects, and we hope also to get a closer tie with the different national programs. And for the flagship projects, we are setting up a steering board which is made up of the representative of the projects. And then, of course, we have the coordination support action that is the facilitator of all the communications, all the interchanges, organizing meetings like this in such a prestigious area, defining or helping common activities of communication, training, etc. So this is just as a summary of the different roles and mandates of the strategic level of decision making. When we set up the governance, we wanted to have something as light as possible, but as efficient as possible to avoid losing too much efforts in discussions at various levels. So, at the end, what we want to achieve is to have a complete quantum ecosystem, where, of course, we have as one major building block the quantum flagship, but this should not be seen in isolation. There are many, many things that are essential to be covered in the area of quantum, but the flagship cannot cover everything. That's why we are working on a good interconnection, cooperation, and complementarity with a number of other initiatives, be it funded from the unit, be it funded at national level, looking at different aspects. I already mentioned the space program. So at the end, we want to have a real ecosystem where each program is concentrating on one key aspect and has the linkages with the others. Now let me conclude with 2 slides on what are the next steps. The projects are launched, so I could almost say this is now history. We now, of course, need those projects to get working together. Let's not forget that we don't have 20 individual projects, but collectively they make a flagship and are addressing a common challenge. Questions on engineering, manufacturing, or even the benchmarking, this is what we will now start discussing with the projects tomorrow. But then there's all the activities that are beyond just the daily running of the projects, which is what comes next. And that's where we invite the whole community, the whole quantum community at large to participate actively in the shaping and the debates. I mean, the ramp-up phase is started. What should be the focus? What are the topics to address after the ramp-up phase? What are the topics that we're going to select? The instruments. Horizontal questions like what are the training, education needs? How can we build the markets? How do we ensure continuity? I mean, it would be very sad if in 3 years, when we go to the next round of projects, we throw away all the things we develop and start from scratch. So that's where we really want the whole community to participate, to shape the future of the flagship and participate in the debates. Now, from an institutional point of view, we are at the end of Horizon 2020. We launched the quantum flagship, and we are negotiating at the political level what comes in the next financial perspective. So the idea that the Commission is bringing forward is, on one side, continue the flagship with a similar objective in Horizon Europe, where we develop the applications that I showed you before, address fundamental science, and really have the technology supply that would then go into more the infrastructure program, which is a Digital Europe program, where the idea would be, for example, to build an experimental quantum computing infrastructure that would be fueled maybe also by a quantum computing mission in Horizon Europe. We're also seeing a convergence between the classical supercomputers, high-performance computing, and quantum. So we would like to develop the first hybrid machines that would integrate quantum processors as accelerators. And then as a follow-up to the QKD pilot, we are launching to have a Europe-wide QKD network distributing services, keys, and so on. Thank you for your attention.
So thank you very much, Gustav. We don't take questions at this time, I'd say. So we heard about the governance of the quantum flagship, and you have probably noticed that there is a new element in this governance called the European Quantum Community Network. Compared to other flagships, I think this is really the new thing. So this flagship should be deeply rooted into the community, and the understanding was that in order to be successful and effective, you need to have the support of national communities. And the chair is with us, so Professor Calarco, the driving force behind nearly everything what has been going on last 10 years in quantum, and I asked him to give some more information on this quantum community network.
Thank you very much. So, well, what should I say? I'm very happy. I think we are all very happy, but there are many challenges ahead of us. This is actually the first meeting that we are having after the selection has been made. And so we have some happy winners, and we have some less happy people which have not been funded by this. And I'm starting my speech by saying this, not because I want to highlight negative things, but just because I wanted to say we need to keep up with energy into the future. And so what I'm going to talk about is how we are going to try to organize keeping the whole community together. Because if we now would have a decoupling between those who are in the projects and the rest of the world, then the flagship will not be able to sail. So it needs to be a big fleet. So let me discuss that. Okay, so this is what I am, again, summarizing. We are in the timeline in which we are. At this point, we are here. The projects are starting. They have been just announced by the Commission. At noon, there will be the embargo finally falling, so you can advertise your postdoc positions. You can say that you are in a flagship-funded project, finally. And so that's good news. And now the question is, what comes after here? And so I would like just to summarize the process briefly, which brought us here. So last time we met, we were in Oberkochen, and there was a big discussion at a symposium organized by Zeiss, not significantly, I mean, not insignificantly, a company, big company investing in quantum. And what we had was a large discussion in different groups, preparing a document, and I was very happy that the Commission is telling me that this document that we wrote as a basis, as an outcome from Oberkochen, has been the basis for the Commission to conceive the new developments, not only in Horizon Europe, but also in Digital Europe, which Gustav Kalbe has mentioned before. So they are really taking very seriously what we are giving here. They are using it as an input for not only the framework program, but also beyond that. And this should be really a motivation for us to keep getting involved in all of this and giving input into that. And I will describe how we are going to do that. So here is again a summary, the 4 pillars, and the basic of basic science, and they all together form the flagship. But now the question is, what is the quantum fleet around it, okay? In the sense that, as we said, there is this framework program, which is Horizon Europe. The current one is Horizon 2020. There is the Digital Europe program, which Gustav has mentioned. There is a space, which he also has mentioned. So how do all our areas connect to what is around? What is the future? I mean, what is the money? Where is the money coming from in the future? You know, here around, there is a circle of what we could call, you know, some outputs. Some people call them some missions which could come out of the flagship, like building the first quantum computer in Europe or developing a pan-European secure quantum network. Those things feed into the Digital Europe program and other applications in terms of healthcare, navigation, and so on, which are relevant in all of these contexts. So there is not only the science dimension, which is the research aspect in the framework program, which deals with our strategic research agenda, which the Strategic Advisory Board is going to develop based on our input, and tomorrow we have a long day of discussions in this direction. But there is also, of course, all the connections to space, for instance, for security, as well as for navigation. But as Gustav has mentioned, in terms of high-performance computing and hybrid infrastructures in this direction, this is the connection with the Digital Europe program. All of these arrows mean money, okay? So here is 1 billion sitting and here is a similar order of magnitude coming out. This is why I'm putting this diagram, okay? So just to understand why I'm telling you. And here is, again, the education side. Oops, the projector. Okay, so education side, so connecting to, Marie Curie programs and so on. This was also a subject of our paper from Oberkochen, which the Commission is taking very seriously, as I understand. And then there is the dimension of member states, which are, of course, connected, not only the board of funders in terms of decision-making, but also in terms of involvement and input with the quantum community network that was mentioned before. Of course, there is the Quantera Euronet, which is going into the second call without Commission support and still with a very broad involvement of member states. There will be a pre-announcement afterwards. And of course, there are also specific infrastructures like Euramet, the European Association of Metrology Institutes, which also is liaising with us for some of these applications, and the European Space Agency, which is now next month near Amsterdam having the third workshop in a row on these topics. And we have seen one of the calls that Gustav has mentioned, and more is coming. And of course, on the horizon, there is the dimension of international cooperation. We had a workshop with Japan in Paris a couple of months ago, and we are having now discussions with the White House about how to pursue further with the US. So, and then of course the big question that one has is who pays the bill, right? And so I would like to show again an important excerpt from a parliament event which I showed in Oberkochen, but not everyone was here, so I would like to document what is happening. I hope there is audio here, yes, right? Yes, I hope so. There is no audio, beautiful. Oh, okay. So, okay. So I will not tell you how much I'm paying for this conference situation here to work with the Hoflieferanten of the Hofburg. I will just tell you what Mr. Ehler has tried to say, is saying. So, which is, he says, this is an event that we had in Brussels a few months ago in Parliament. He says, the last remark from my side, concluding this argument, regarding quantum, you have heard the statement by the Commission that they will invest 1 billion euros, and the Parliament is ready to pay the bill. This is what he says, and you can see Bill here, Bill Phillips, Nobel laureate 97, who of course is smiling very happily. So this I put on also to show that really, there is not just, our own friends in the Commission, DG Connect, the people who have made this thing grow, but which want to support it. Not only member states want to support it, but at the highest level within the European institutions, including Parliament, there is broad support for this. For instance, okay, so I was able to suggest to the ITRE committee, which is the committee which is going to approve Horizon Europe, some nice amendments, which is very technical. It is some fine print, but if you go here, there are 9 zeros, okay, which they accepted to put, including 3 billion euros for continuing FET flagships. This is a very big issue. It might seem, administrative, but if you take your cell phone and you go to, of course, you are not going to find this on an official Commission website, but there is a leaked document in the Science Business blog, and this leaked document shows you that there are a few topics which are going to be discussed in the Council of the European Union for possible missions. And one of them is a universal quantum computer. But this is by no means a trivial thing, because then the question is now, will the flagship continue? Will a mission on quantum computing come out of the flagship, which is much broader on quantum technologies? Is there a danger that if they do a mission on quantum computing, then there will be no more flagship? So all of this is being intensively discussed, and our DG Connect is very strongly supporting, and our Commissioner Gabriel is supporting very strongly the continuation of the quantum flagship, but this is something for which we need to gather broad support, not only in Parliament, but at the level of each member state, because the discussion is happening next week in the Council of the European Union. So we still have to do a lot of work to make sure that this survives in the best possible form in the future. So this is just, stay tuned, especially for our QCN, our Quantum Community Network, to help in this process and support the continuation of the quantum flagship. Another nice amendment, I would say, which is here that the Parliament is putting into the report, is to include quantum technologies as a key enabling technology next to things such as artificial intelligence, robotics, and so on. So this is also very good news, I would say, for us, and it may mean a few more 9 zeros numbers adding to the whole thing. So I wanted a quote. okay? And I got an email with this quote from someone. Actually, it is someone who wrote some time ago something which is very fitting for quantum, which is the essential is invisible to the eye, right? His Holiness the Dalai Lama knows that it is not entirely invisible after he went to Rainer Blatt's lab. But okay, so this is a quote, and then it says, if you want to build a ship, don't drum up people together, it's a ship, yeah, to collect wood and so on and so forth, but rather teach them to long for the endless immensity of the sea. And I thought, oh, what a beautiful quote. But I know that in the internet there is fake news, right? So I checked, and actually this is not a quote by Antoine de Saint-Exupéry. It is something which is in some attributed to him in some handbook for management. So I went for the real quote. And then this is the real quote, which I think is actually better. In the beginning, I thought, oh my goodness, you know, it's not about weaving canvas and so on and so forth. And he ends with, you know, you will see nothing contradictory, but rather a community of love. And I thought to myself, oh my goodness, am I going to speak about a community of love in the Vienna Hofburg? But I thought, well, maybe it's not so unfitting, because the task that I've been assigned was to speak about networking activity of the quantum community, and it's not about we love each other, especially not after some people got the project and some didn't, but we do love what we do, yeah? So I can certainly say that all of us, and I should say not only the scientists and industry people, but really also the people in the first row here, you know, from the European Commission, we really all love what we do. So, I mean, this is a good basis, I would say, for the next things. So here are some pictures of people who really love, you know, serving the community and helping to create the next wave of activities. And so I'm going to go quickly through the activities that we have been doing and that will come next. So from work package 1 about strategy, this is about gathering the whole community. Tomorrow there is a big discussion on this, but also there is the conference in February organized by COA. And here we see the collaboration between the current coordination action and the future one. And so we have working groups formed, and via the qt.eu website, we are going to be able to have the whole community involved, and we are going to launch this in the next couple of weeks. So this is about getting the whole community giving input into the strategy for the future, which then will be decided upon by the Strategic Advisory Board. And then there is also the new strand, which for our community is growing, as Gustav said, about innovation, involvement of industry. So there is an innovation working group, which also we'll discuss tomorrow. There has been, as I mentioned, this international cooperation workshop tied to Japan in recently, a couple of months ago. So this is also another strand, an additional strand of discussion and input that we are going to organize, and it is going to continue also in the next coordination action Q-Flag, which Marcus Wilkens is going to coordinate. So this is just one deliverable that we have. You will find all of this on our website. Our website is now going into version 2 in a couple of weeks. It will be there. It will have much more functionality, really for involvement, for gathering input, for you know, database of groups, information channel for informing everybody of what is coming up. So this is the next thing up in our agenda. And, well, this is the input that we gave to the Commission for the governance. This is a deliverable that we gave to them. You see, you know, with this, all these bodies, which Gustav has also mentioned before, like this whole community coming together with these all different functions. So this is how then, and I'm just repeating a slide that Gustav showed, which, you know, has this governance structure, again, with this very important addition, which is very new, as was mentioned before, the Quantum Community Network, next to the other bodies. And the Science and Engineering Board, which is the project's coordinators, will meet for the first time tomorrow. And so then we are going to be able to work full speed with the support, secretarial support, the secretariat, so to say, of the flagship, which is going to be the coordination and support action. So these are the people who are going to run the future coordination and support action starting from March. They are going also to run the day tomorrow. And this is what we are going to do tomorrow. In parallel, there will be the discussion of the Science and Engineering Board. The first, of course, this is a closed meeting because this is just the internal discussion between the Commission and the contractual partners running the different projects. And the whole community, so in parallel, we are going to do, at the same time, we are going to have a whole day of discussions about input, what we can, how we want the flagship to look in the future. And well, it starts slightly earlier than the Science and Engineering Board, so we have half an hour in which we can be all together in the same room, so to say, to start, you know, seeing how we want to go into the future. And then I guess that's it. So another quote from the same guy, which I think is very fitting for our coordination action. Our task is not to foresee the future, but to enable it. And so I think this is what we did in the past 15 years. We are going to do it also for more than the next 15 years. Thank you very much.
Okay. Thank you very much, Tommaso, for this lively talk. We are now coming to the real projects. We have talked about it several times this morning, and as you know by now, 20 projects have been selected by the European Commission, and we have grouped them into 4 areas. In each of them, also the fundamental science projects are included. And we ask one of the project coordinators to present the whole area. And I would like to start with Professor Stephanie Wehner to give some more detailed information on the project on quantum communication.
Yeah, thank you very much. Good morning. It's a great pleasure to be here at the start of the flagship. I'm very excited about this. My goal in this talk is to give you an overview of one of the pillars of the quantum flagship, namely quantum communications. So in quantum communications, our goal is to fundamentally enhance communication technology by enabling the transmission of qubits. So unlike the classical bits 0 and 1 that we send over the internet today, our objective is to send quantum bits or qubits. And as many of you probably know, these qubits can be both 0 and 1 at the same time and have pretty cool features, one of which is that they cannot be copied. And in fact, attempts to do so can be detected. And this makes qubits very naturally suitable for applications that require security. As was just mentioned, you know, we want to enable things, so it's very difficult to foresee all applications of quantum communication in the future. But there's already quite a few interesting ones. So probably the most famous reason why we work on quantum communication is secure communication. So quantum key distribution, or QKD, has the property that it prevents an eavesdropper from intercepting your secret messages. And QKD is secure even if that eavesdropper has a quantum computer, now or in the future. So in QKD, security rests on the fundamental properties of nature and is fully future-proof, even to some era where quantum computers might be widespread. Quantum communication has a few other cool applications, for example, to do secure quantum computing in the cloud. So you might imagine that maybe at some point, we actually have quantum computers that are offered by someone as a service and that you might want to use in order to perform a simulation, for example, from a proprietary material. Quantum communication enables you with a very simple quantum device to use this remote quantum computer in such a way that its owner can neither learn what material you want to simulate, or in fact that you're performing a simulation at all. Quantum communication can do various other nice things already. For example, clock synchronization, password identification. People have even proposed protocols to coordinate at online games, and many more. Quantum communication also offers a path towards scalable quantum computing by taking small quantum computers and linking them together into one larger quantum computing cluster. It's important to understand that quantum communication is actually already reality now. At short distances, roughly 100 kilometers in fiber, and for simple but very nice applications like quantum key distribution, we can actually already do that today. So commercial devices already exist that solve this task. In quantum communication, we in fact can already do things which are provably impossible classically by preparing and measuring just one qubit at a time. So of course we want to do much more in the future, but there is a very scalable path, or a gradual path in fact, from doing things which already are commercially available now to a faraway quantum internet of the future that enables many more applications. So what are our objectives in this pillar? So I already said that quantum communication is actually already reality now. So one of the objectives is to make cheaper, faster and more reliable devices so that many more people can already use quantum communication now. On the other hand, we also want to increase functionality by connecting ever more advanced systems to such quantum communication networks over time. We also work on application software because we want to make what's happening here actually useful to end users, and develop a software stack so that software developers can write software for our quantum networks in platform-independent software. One of our objectives is to build quantum repeaters. And the objective of a quantum repeater is to transmit qubits over long distances. Initially, we hope pan-European distances, but maybe in the future, from any 2 points on Earth. We also work on a network stack to enable fast and reactive control of such a network, and technology that maximizes the use of the telecom infrastructure. For example, switches, which more people can already make use of such quantum communication technology. We work on these objectives in 4 complementary projects. And in the remainder of the talk, I want to explain to you how these projects fit together in order to attain our objectives. So the first project that I want to mention is QIA, the Quantum Internet Alliance. And the Quantum Internet Alliance targets the long-term perspective on working towards a quantum internet. Its main objectives are work towards a quantum repeater to send qubits over long distances, and in fact to connect more advanced quantum processing systems to such networks, not just to be used as repeaters, but also to support more complex applications. QIA develops real-world use cases and also examines the hardware requirement for implementing specific quantum protocols in order to guide implementation. We target the demonstration of the first demonstration of a software and network stack for such quantum networks, and the first demonstration of an elementary link of a quantum repeater. We want to, in fact, link for the first time several quantum processing systems together into a quantum network, and also connect such quantum processing systems to quantum repeaters going forward into the next phase of the flagship. So it's very important for us, in fact, also to find out how we can actually go beyond what we're doing now and how we can scale into the future. So an important outcome of the QIA is, in fact, a scalability analysis or a blueprint for a network architecture with which we can cover large areas in the future and validate this architecture in simulation. QIA is a collaboration between world-class research institutes in physics, computer science, and engineering all across Europe. QIA is coordinated by QTech, in this case myself. We work with industry, in particular, to engineer components for a quantum internet. And these are quite diverse, ranging from laser systems to cryogenic systems. We work with industry to examine real-world use cases of this technology, and an RTO, in fact, to bridge that gap from research to applied technology. We work with supercomputing facilities to actually perform these blueprint simulations. And we work on engaging and communicating with the classical internet community via the regional internet registry of Europe. We've actually already held a hackathon on the 13th and 14th of October, where we've invited, actually RIPE has invited people from the classical community to already start programming things or exploring applications on such quantum networks. Because of course our goal is to go beyond the little group of quantum people that is here and engage many other people that are out there. And in fact, I guess our future objective is to minimize our own involvement in a much larger ecosystem of developers. We also engaged with network operators that give perspective on service provider and fiber, connections to QKD industry, and also end user perspectives. Okay. Very complementary to this is the project Unicorn. So Unicorn works on short distances and sort of simpler quantum devices, but it's very cool in that it tries to make quantum communication actually affordable and accessible to everyone on a short scale. So the objective of Unicorn is to create smaller, cheaper and faster quantum devices by developing semiconductor quantum optic communication components, with the objective actually to go away from breadboard demonstrations on performing quantum communication on chip, potentially in the future also integrating such chips in IoT devices. Unicorn works on demonstrating scalable key subsystems and also developing deployable system performance and novel network functionalities. For example, working on low-loss switches, which form an essential component of actually all future quantum network activities. Unicorn also wants to demonstrate low-cost quantum links in the lab and in the field for QKD, and also already other sort of simple prepare and measure applications in the real world. Unicorn has partners from academia that work on, of course, bringing necessary expertise from physics in both theory and experiment, design, automation, and simulation from industry, RTOs that turn basic science into applicable technology, and the coordinator of Unicorn is AIT, Hannes Hübel. Industry to perform assembly and packaging, telecom systems integration, industrial end-user perspective to actually inform further development, and a collaboration between both industry and academia to design photonic integrated circuits for performing quantum communication on chip. The next project in the quantum communication pillar is called CIVIC, and its name stems from the fact that it uses continuous variables, which is a different quantum encoding, hence the name CV. And this may have advantages because it offers the potential to be sort of benefit from existing technologies developed for widely deployed coherent communication systems. And CIVIC starts by actually taking requirements and specifications from the telecom industry in order to develop flexible and modular and network-aware QKD systems. So network-aware here also referring to, for example, using software-defined networking in order to control such devices. CIVIC also targets the development of high-performance QKD components and systems and wants to validate and benchmark them over datacom and telecom infrastructures. CIVIC is also looking ahead to kind of beyond what's coming beyond, and is investigating, for example, how to go beyond the point-to-point regime, and also how to perform uplinks of such quantum communication links to satellite-based networks. CIVIC involves a collaboration between telecom operators that forms a connection to end users, industrial equipment and system integrators, industry that works on component and subsystem manufacturing, as well as research institutes and universities across Europe. And CIVIC is coordinated by ICFO, namely Valerio Pruneri. The last project in the main pillar is called Q-Range, which delivers a key, actually enabling technology for all of the other efforts in this pillar. In particular, Q-Range works on quantum random number generators. And you want to have quantum random numbers if you're, for example, implementing quantum protocols such as QKD, but they're, of course, much more broadly interesting. And in fact, Q-Range here specifically aims to investigate not just a system architecture, but also more use cases of actually truly quantum random numbers. An important step in sort of bringing these into the real world and actually getting them used is the work on a certification framework, where Q-Range is working on proposals to extend AIS 31 PTG to a standard that is actually sort of generally quantum, and that may in fact take concepts from quantum, namely self-testing quantum devices, really as an integral part of such certification procedures. Q-Range works on concepts and theories, in fact, to test such devices, and targets the sort of construction of 3 different prototypes for producing random numbers. One of them is going to be compact and cheap, for example, for IoT devices. The other one is extremely secure. And the last one is very fast. Q-Range works on this together with research institutes and universities and also industrial partners in order to realize these 3 different types of prototypes for producing quantum random numbers. Finally, the quantum communications efforts involve 2 projects from basic science that target photonic integrated circuits. And this is very nice, as already mentioned, because it can allow to put quantum communication systems away from sort of breadboard setups to systems that can be realized on chip. The first of these is S2QIP, which is coordinated by Klaus Jöns from KETH, that targets foundry-based large-scale CMOS-compatible photonic quantum circuits, and in particular the integration of 2D materials on such circuits. S2QIP also works on on-chip nonlinear optical frequency conversion and on-chip on-demand single photon emitters. The other such project is 2D SIPC, which is coordinated by Dimitri Efetov from ICFO, which works on broadband and high-temperature single photon detection, very fast single photon processing, as well as tunable and entangled single photon emitters. And the objective is to, I guess, combine these, in fact, on one chip, to perform a demonstration of on-chip all-optical quantum processing. And this can be useful, of course, for quantum communication, but also for quantum computing and quantum simulation efforts. So over lunch, there's a poster session where you can learn more about these projects. Thank you very much.
Thank you very much, Stephanie. Now we are coming to the area of quantum computing, where Frank Vellamo will present the area. Frank was also involved as chair of the organization committee of this event, and so I'd say give him a warm welcome. Well done so far.
Yes, thanks. Yes, my name is Frank Wilhelm, and you all have emails from me. But I'm not here as the organizer, but to talk a little bit about the quantum computing pillar. So when we talk about quantum computers, we talk about speed up of computational tasks. That is not the speed up that you get from your electronic store catalog with the next faster clock. Speed up for quantum computers means that the effort, the time you need to invest in a computation grows slower than on traditional, what we call classical computers. And that often means that only with quantum computers problems become efficiently solvable. An interesting example for this is cryptography. So your keys are secure because whenever somebody builds a supercomputer that is enabled to decipher today's cryptography, you make the key slightly longer, and it will again be undecipherable because it will take millions of years, and this arms race is always won by the person posing the problem. And when we talk about speed up in quantum computing, we mean this type of different scaling. How do quantum computers do that? Well, if you look at today's supercomputers, the main driver of supercomputing performance is parallel execution. But for each strand of parallel computing, you actually need to build a new parallel device. A quantum computer can take binary input and then create a superposition of all possible values of the input data, and then work simultaneously without any parallel CPUs. It can do this on a single quantum kernel, and it can be as parallel as you need it. But the caveat is quantum physics has a randomness to it. So at the end of the computation, you want to get rid of the superposition so you have a meaningful outcome. And that is not easy, but there are solutions, there are algorithms that can harness this. Now, what is the quantum computer you run this in? Here is a symbol. And we currently see a plurality of platforms also in the Flagship program. And this is not something that is very unusual. If you look back at classical computing of the 1940s and 50s, there was a plurality of platforms. We went from mechanics over electromagnetics to tubes and transistors. And also, initially, classical computing was very similar to what today we call supercomputing. in the sense that you probably did not have one of those at home, but you certainly benefited one of them. We should not forget that World War II was probably shortened by the use of classical computers. So the applications are the hard applications of computer science. They include artificial intelligence, training of artificial intelligence, database search, optimization, routing. These are the problems from the machine room of modern supercomputing. In quantum computing, I'm now telling you a little bit how this is approached in the Flagship based on two pillar projects, Action and Open SuperQ. I'm the coordinator of the latter, and three basic science projects that go with it. If you look at those from a bird's eye perspective, what are the challenges? So the pillar projects are all aiming on what you can call the quantum advantage threshold. At a number of 50 quantum bits, a very modest number compared to the gigabytes we're used to, you can reach something that is called quantum advantage, in the sense that your quantum computer cannot be simulated by a classical computer anymore. So in the most ivory tower application you can think of, it's outperforming our classical computers. And if we go beyond this, we can make it possible to harness this. These projects work on two different platforms, but what they have in common is that they want to really go from a device to a machine and develop the whole stack from qubit to end user in hardware and software. And they want to make quantum computing available either in the cloud or as a portable service. Now, the basic science projects that explore hardware alternatives within those platforms, and one alternative platform, what all of those have together is that they are very much looking at lowering the error rate of quantum computers, which is as important as having enough qubits that they actually work reliably, that they all tackle the challenges of scaling from basic components that are already shown to work if you only have a few of them, and they all develop a technological ecosystem of supporting technologies around it. In the Action project, this is done with trapped ions, and their goal is to have a machine that can be taken out of the lab, that can be put into these racks, with here an ion trap, with a laser system, with all the control software. So there's a full software that also allows to verify and validate that the quantum computer is doing what it's supposed to do, and that can be taken outside the lab of the people who built it. So it is dealing a lot with making all the technologies available on the 50 ion scale. That includes lasers, that includes the classical electronics around it, the fabrication of the traps, and also the software, including compilers. So they will deliver this task, and they will also be able to optically interface to remote ion traps, very much connected to what we just heard, and want to go beyond this, so this can be purchased and moved around. And these are the partners. MicroQC is a basic science project that also looks at trapped ions, one of the leading platforms, but wants to do as much as possible, not with lasers, but with microwave sources, pack everything into a compact chip layout, and use these reliable off-the-shelf microwave components as much as possible. For this, and specifically for making everything precise and reliable, they have a strong integration with theory that makes sure they're doing the operations in an optimal way, and then go beyond this to see how this merges with the other part of the effort. So they use microfabricated traps, they use microfabricated chips, they integrate, which for me as a theorist is particularly important, they use optimized strategies to make those gates and explore several options in this. These are the partners, Nikolai Vitanov from Sofia is the coordinator. And I should have said in the first project, Thomas Mons from Innsbruck is the coordinator. Open SuperQ now goes to another hardware platform. So this is the Open Superconducting Quantum Computer. We are using computer chips made from superconducting materials with qubits containing junctions that then can be put onto a chip scale, so at each crossing here of a qubit, then packaged into a device and then operated in a low temperature environment. Here the goal is to not build a portable quantum computer yet, but to make quantum computing sustainably accessible as a cloud service, as a supercomputing service in a Central European laboratory. Again, we are aiming for long coherence, and we would like to develop not only the operational quality, but also demonstrate that we can do meaningful quantum chemistry and optimization applications on it. Again, there is a whole stack development related to this. So we take the individual components that we know we work and put them into a really big machine. We engage with the end users, and we build this machine in a distributed way and then assemble one in the central quantum computing lab, which we sometimes call the Airbus method. You know, somebody makes the wing. I think Airbus doesn't work like this anymore, but they used in the beginning. So we're making different components and assembling this. And we're also developing specifically chips, package, amplifier, and electronics engineering ecosystem around that. And these are the partners. QMix is looking at the same platform. You can see posters in the room back then. QMix is taking the same platform, but looking specifically at the long-range communication effort. Long-range microwave links between cryostats, which look like this, and they're looking at the measurement infrastructure. And this will not only help to make even larger superconducting quantum computers in a more integrated lab, it also has an interesting connection to sensing and communication, for example, in the area of quantum radar. So they're building the 6-meter-long millikelvin link, and they are developing microwave single photon detection, amplification, and continuous variable technology, and thus, as was mentioned this morning, are also bridging to our neighboring pillars. Again, these are the partners, and some of them are here, and they are at the poster. Now, Square is exploring, beyond these two platforms of ions and Josephson junctions, a third important platform, namely rare earth ions, as an optically addressable register. And they want to show that it can be a viable and interesting quantum computing candidate that can be scaled, specifically that many of them can be packed into a compact volume, and that they have an attractive spin-photon interface, which again is important also for engaging them in cryptographic infrastructures as mentioned in the previous talk. So again, also Square is linking computing to other pillars. So these are the partners. So what are the common challenges? The common challenges is scale-up science. We have devices that work on a small scale, but we need to go bigger. And bigger means that we go outside what traditionally basic researchers and universities can do, but we are still much below what typically is a worthwhile economic perspective for a big company, so we need to explore this space. Physically, the biggest challenge is to maintain the low error rate and the high precision of operations while we are scaling up. Make these scaled up qubits at least as good as the best qubits we had before. Those are typically big science style projects, so we're typically building one device together. And we are, of course, competing in an area with also major non-EU players. There are contact data, which I'm just showing you because I'm running out of time. So Innsbruck is coordinating the ION project action. Sophia is coordinating MicroQC. I'm coordinating OpenSuperQ. QMix is coordinated by Frank Deppe of the Walter Meissner Institute. And Square is coordinated by David Hunger at KIT. I'm sorry to the partners who have rushed through, but we need to keep on schedule. Thank you very much for your attention.
Thank you very much, Frank Willem. And now I'm looking for Augusto Smerzi. Oh, it's already here. Okay.
So, ladies and gentlemen, good morning. My name is Augusto Smerzi from the CNR and INO Institute in Florence. I discuss about the quantum simulation pillar. So why we need a pillar on quantum simulation? Well, the reason is that our macroscopic world, the world where we live, interact with objects and people, is very small. It's just a tiny fraction of the world where quantum objects live and move. They move in a huge, abstract hyperspace. And when I say small, I mean small in terms of the capacity of store and manipulate information. So what is the consequence of that? The consequence is that if you want to study a quantum system with a classical device, we'll need an exponentially large number of classical components. And when we say exponentially large, means impossible, typically. For instance, we need a system which should be much, much bigger. For instance, the largest ever computer built, which is the ENIAC probably, which was huge and heavy, but in terms of computational abilities, was of course very pure. Okay, so we have a problem, and now we need an idea. And the idea came at the beginning of the 80s by people like Feynman, but also by others, who thought that let's say the computer or the device itself built on quantum mechanical elements rather than classical elements. Okay? Quantum mechanical elements which obey quantum mechanical laws. So what is a very good idea? Well, simply because the quantum device now can contain a small number of components and still manage to manipulate a huge amount of information. And then came the vision, a quantum simulator. So what is the definition of quantum simulator? A quantum simulator is a quantum system which can be built in a laboratory, but that you can tune and control accurately, okay? You can manipulate it, so to simulate other much more complex quantum systems. So this is a simulator. So what is the main advantage of quantum simulator with respect to a universal quantum computer? Well, as you can imagine, simulators are task-oriented. So you have a problem, and you build a quantum mechanical system in your lab to solve and study this specific problem. Okay? While universal quantum computer, of course, can be programmed to solve any sort of problems. So quantum simulators are much simpler. Of course, there are some drawbacks, and the main disadvantage is that we don't have. I think this is my previous presentation. This it's not my last version. Just a second. Can you check the last slide, please? No, this was not the last one.
It's not your projection? It's Mercy, yours, Mercy.
Yeah, but these are sent to the new one. Can we use my computer?
Did you want to tell me that Sunday was a different version?
Yesterday.
Well, I thought you had resent it. Sorry. This is not the last version.
Yeah.
Sorry about that.
No, it's okay.
Cosa c'è dentro di diverso?
È diverso il coso.
Quello quanto?
Abbastanza.
Ma non abbiamo tempo.
Just un secondo.
Proprio non ce la facciamo, ci sono 500 persone che stanno aspettando. Non possiamo. Ok.
Viene presentato, it's done. Quantum simulation ho fatto. Yeah, questa è. So, where is it?
No, facciamo andare Shrek.
No, è fatto. No, è fatto.
Jetzt haben Sie den Ton angeschaltet. There is sound.
Yes. quantum simulation one. Can you go? Yes, this one. Yeah. Okay, so sorry for the inconvenience. So we are going back to advantage and disadvantage. So the main advantage is that quantum simulators are much simpler to build, as I was saying, because they're task-oriented. On the other hand, the disadvantage is that we don't have a general protocol for quantum error corrections. While universal computer, you can always be confident about the results of your, the fidelity of your results. Here in quantum simulator, you always have to think about specific protocol to test the correctness of your result. Okay, so what you do with a quantum simulator? Well, you can study high-energy physics, like simulate lattice gauge theories, or you can study high-TC superconductivity. There's a very long list of problems that you can study. What will be the impact? Well, this is called quantum supremacy. To me, this is what? Is the point where you can solve problems and understand the world with radically new tools. But not only that, will be the point where you understand the world with a radical new way of reasoning, okay, based on the quantum mechanics. Okay, so in the pillar, there are two projects in the quantum simulation pillar, which I will introduce briefly, and two associated projects from the basic science. So the first one is PASCANS, with the coordinator Emmanuel Bloch, Antoine Brouillet. The second one coordinated by myself, then FOG, coordinated by Natalia Korolkova, and FOCUS, coordinated by Alberto Bramati. So PASCANS, this is the first project I want to discuss, includes 10 university and research institutes and 5 companies with a few associated end users. And the institutes and the company are distributed geographically on the yellow parts of these geographical maps. So what is the goal here? So this is how a quantum simulator is built in practice. They suggest 5 different platforms. All of them are based on atoms. So for instance, you can trap the atoms in an optical lattice, and you can observe singularly each atom and manipulate singularly each atom. And then you can also try to tune the interaction between the atoms. You have like bosons, fermions, you can use Rydberg atoms, or you can trap the charged atoms, ions. Okay? So this is a general scheme for a quantum simulator. Have control of a singular elements, tune, measure, and tune the interaction between the different atoms. So they have as an objective, of course, to create a very large simulator, more than 500 atoms. And they want to develop a certification of quantum simulation. That's what I was telling before. So they want to certify the confidence, the fidelity of the results. And then they also collaborate with some end users, I shown before, in order to identify the practical industry-relevant problems that they want to address. The second project is COMS, coordinated by me, which include 5 different institutes and universities, and 5 different companies distributed on the yellow sides of this geographical map. So the goal here is to realize a quantum simulator platform made of atoms to simulate a quantum cascade laser frequency comb. So here we are thinking about create in the lab an atomic device, an atomic simulator, to understand a real device. A device that already exists, is already sold by industries, is quantum cascade laser, but our goal here is to create, improve the possibility to create non-classical light with such device. So the device is a laser which sends a comb of different frequencies I want to prove that each mode is non-classical, each mode of light, and there is entanglement between the modes. So the applications here goes from advanced free space communication to high sensitivity detections of pollutants, and there are some applications also on health monitoring. The FOG project comes from the basic science, which include 5 different universities, here on yellow. And this project is also devoted to the creation of non-classical light. The difference is that the laser input, is classical lights, go through a non-classical crystal, okay, with some nonlinearities on it. And the output, you have non-classical lights. You can have, even in this case, squeezing on each mode, sub-Poissonian fluctuations, and entanglement between the modes. And so one among the possible deliverables is one possibility of quantum networks, the possibility to create a net of nodes and link, which is actually quite interesting for many applications like a quantum learning machine or something. And there are applications, of course, for imaging, entanglement, enhanced imaging, atomic clocks with the lasers which are much stable than currently used, and broadly speaking, it could be relevant for metrology, for precision measurement. The last project that I introduced is Focus, which include 9 different institute universities in yellow. And Focus is devoted to the study of quantum fluids of light, okay? So it's possible to create a superfluid made of light. And in this project, the goal is to control the phase, the velocity, and the density of these superfluids. So what will be useful for? Which has been shown that with these systems, you can actually simulate quite completely different problems, like you can simulate the black holes or the Hawking radiation, or you can study also the interplay between undersea localization and interaction, many body localization, which is a typical problem of condensed matter. Okay, so this is more or less the overview of the quantum simulation pillar, but I want to finish by saying that everything started in the 80s, the beginning of the 80s. This Feynman idea and other different technologies were fought. Some did work, some did not work. Okay, so the beginning was really trial and error attempt. But we have a long way ahead of this, first pioneering investigation, right? So it's time to build. And so this, I would like to say thank you for the opportunity and thank you for your attention.
Thank you very much, Augusto. So now we're coming to the last part, the last pillar. It's quantum metrology and sensing. And, well, welcome, Florian Frick.
So, good morning. Thank you very much. It's a great honor for me to present the sensing and metrology pillar to you. Sensing and metrology is really important. It's at the foundation of our ability to understand the laws of nature and to analyze the environment and take data on it. And obtaining good measurements is required to take good decisions. Think of climate change or a doctor who has to decide on a good treatment. Sensing also enables applications such as navigation, healthcare, networks, Earth observation, data storage, and much more. And measurements, even quantum measurements, are cornerstones of many products. Now, in the context of the quantum flagship, you might ask yourself, what are the advantages of quantum measurements compared to classical measurements? And to understand this, I'll give you a task. Build the best clock in the world. And if you only know about classical physics, you will probably build a pendulum which gives you the frequency reference, which makes your clock tick. And this comes with quite severe disadvantages. You will not be able to build two clocks which tick at exactly the same rate, because these pendula are macroscopic objects. Even if you try as hard as you can to make two absolutely identical, you will fail. And these pendula will tick with a different frequency. In addition, they are very sensitive to environmental noise, and they will change their frequency with temperature. Now, luckily, we are living in a quantum world, and the quantized energy levels of atoms provide us with a solution to these challenges. If you look at a specific transition in an atom, then you need electromagnetic radiation of a very specific frequency to drive this transition. And you can use this frequency to make your clock tick. And the beauty of this approach is that if you have, say, a strontium atom here in Vienna, or one in Beijing, or one even in another galaxy, clocks based on these atoms will all tick at the same rate. They will all function in the same way. And also, these atoms are much less sensitive to environmental influences than classical pendula. Now, this is a general topic of quantum sensors. You can make them of identical particles, not only atoms, also molecules or impurity centers in solid states. These sensors can be very small, down to the scale of a single atom, so you can make measurements with very high spatial resolution if you want. You can choose transitions that are very sensitive to the quantity that you want to measure and insensitive to other quantities. Now, this has been explored, of course, since decades, and still there is a lot of progress being made on this technology every year. And now we are in the age of the second quantum revolution, and we can exploit this to build even better quantum sensors. We don't have to only rely on quantum states that are given to us by nature. We can engineer quantum states, reach superposition states or entanglement, and we can optimize these engineered quantum states to enable us to build quantum sensors that have higher sensitivity, a better signal-to-noise ratio, or that disturb the system that we want to measure less, or enable us to build simplified sensors. Now, the quantum flagship wants to advance the research on these sensors and also bridge the gap from lab to applications. And 4 projects have been selected in this pillar to do so: Asterix, Metabolix, Maximal, and my own project, IQ Clock. Now, Asterix and Metabolix both rely on so-called nitrogen vacancy centers in diamond. Asterix is using it as multi-purpose sensors. Metabolix is using it to enhance their sensor. Now let's dive into this a little bit more in detail. What is a nitrogen vacancy center in diamond? A diamond is a crystal lattice of carbon atoms, and if you replace one carbon atom by a nitrogen atom, you will obtain a special structure which contains electrons that behave quite similarly to the valence electrons of atoms, which means you have very well-defined energy levels, and you can drive these structures with lasers and use them as sensors. They have a long coherence time, even at room temperature, and they are, of course, solid-state systems, so they are quite robust. You can also deposit the NV center in your diamond with a position control at the nanometer level. Now, Asterix is exploiting this to build sensors for magnetic fields, electric fields, temperature or pressure, which are very precise and which can work even in environments in which other sensors would fail to operate correctly. Asterix is addressing 4 societal needs: the need for better electric cars, optimized communications, new drugs, fast diagnostics, and energy-efficient electronics. And they are doing this by bringing us closer to solutions, such as improved batteries, the ability to investigate the structure of single molecules, spin-based electronics, and new sensors. So the specific project objectives of Asterix are to build a lab on a chip where little NV centers are placed next to microfluidic channels, which will enable you to analyze single molecules with nuclear magnetic resonance. They will also put NV center on the tip of a cantilever and use it as magnetic field sensor. By scanning this cantilever over a solid state surface, they then can analyze the magnetic properties of this material. They will embed NV centers next to a microwave transmission line, and in this way build a highly precise spectrum analyzer. And they will also build current sensors with high dynamic range. Asterix has built a large consortium of 23 partners from 8 countries, which address all aspects from material development till applications. Now, Metabolics is also using NV centers, but this advances from alone. So, Metabolics is performing a special type of nuclear magnetic resonance imaging to investigate, for example, if tissue next to the heart is healthy or diseased. And they use NV centers to enhance this specific type of magnetic resonance imaging. So how does this work? Their sensor is pyruvate, a molecule that is natural to the body. A patient is injected with a dose of this molecule, and a standard MRI machine can then determine the distribution of this molecule in the patient's body, which gives you insight on the metabolism that is happening in the body. And the system is not working just as simply as I have shown it here. You have to polarize these pyruvate molecules before injecting them into the body. Why is that? Magnetic resonance imaging is not directly giving you the density distribution of these molecules. It's rather showing you the difference in the density distributions of molecules in 2 different internal states. And if you rely on normal thermal excitations to enable this different population, then you will have only 1 molecule more here in the lower state for 100,000 molecules in your system. That means you're wasting a lot of your molecules. Now, with hyperpolarization, you can bring most molecules into just one of these 2 states, amplifying your signal by a factor of 10,000. There are already machines on the market which produce this hyperpolarization, but they operate at temperatures of liquid helium, and preparing just 1 dose for a patient takes many hours. Metabolics has a great idea to use diamond NV centers to perform this polarization. Essentially, they will polarize the electrons in the NV centers using lasers by optical pumping, and then transfer this polarization onto the nuclear spins of the pyruvate molecules by just flowing these molecules close to the surface of the diamond. And this works at room temperature and continuously, much faster, so you will be able to prepare many more doses for patients than with the old-fashioned method. And they have also established a consortium that unites all the expertise that you need to lead this project to success. Now, the other 2 projects rely on atoms to build sensors. Maximal will use atoms in miniature gas cells for multi-purpose sensors, and we are cooling strontium atoms to ultra-cold temperatures to build optical atomic clocks. Here you see the Maximal consortium kicking off their project. They come from 14 partners in 7 different countries, and they are very excited because they will design advanced quantum-enabled sensors which measure physical observables in 5 key areas: magnetic fields, time, rotation, electromagnetic radiation, and gas concentration. All these sensors will be based on one core technology, MEMS atomic vapor cells. And this consortium tries to contribute to establishing European leadership in this industry and drive excellence in quantum technologies. So Maximal will bring us new sensors with greatly improved performance. And they will reach this by combining MEMS atomic vapor cells with state-of-the-art quantum sensor physics. Here you see such a miniature vapor cell. It's just millimeter in size, a vacuum chamber filled with, for example, rubidium atoms. You can send laser beams or radio frequency radiation through to sense the state of the gas. And this manner of building the sensors allows for high volume, high reliability, and low-cost deployment. Maximal will target pre-industrialization of 3 quantum atomic devices: miniature optically pumped magnetometers, miniature atomic clocks, and miniature atomic gyroscopes. They will also explore novel architectures for quantum and performance-enhanced future atomic devices. They are also including atomic gigahertz and terahertz sensors and vector emitters and Rydberg-based gas sensors. And they cover the whole development chain from basic research to industrialization with this consortium, including 2 RTOs, 8 academic groups, and 4 SMEs in industry. And if you want to know more, you can contact Jacques Hessler from CSAM. Our project is using ultra-cold strontium atoms to build optical clocks. Here you see this heart of such a machine, and this fluorescent cloud of strontium atoms is levitated in the vacuum chamber by laser fields. And we will interrogate an ultra-narrow transition in these strontium atoms to build optical clocks. The best clocks that work after this scheme have an amazing accuracy. They go wrong by only 1 second of the age of the universe. And we want to bring part of this performance from the lab to society and also demonstrate a novel type of clock which might lead to simpler products. And we want to do this because clocks are absolutely crucial for network synchronization, positioning, astrophysics, and optical atomic clocks will make these applications better and open up future applications. For example, geodesy. If you have 2 clocks and you compare their frequency and you lift 1 clock up by 1 centimeter, you will see that the relative frequency of these clocks changes just by the gravitational time dilation. If you put these clocks into space, you can sense gravitational waves, and perhaps we will be able to answer the question, do the fundamental constants of nature change? In the affirmative, and that would give us hints of physics beyond the standard model. Now, to bring optical clocks from the lab to society, we will have to overcome some challenges. The first is that optical atomic clocks are large and fragile. Here you see a clock in the lab of our partner in Torun, Poland, and this, I can tell you, is one of the neatest atomic clocks that exists in the world. And still you can see that it is not easy to transport this clock. Therefore, we will use the expertise of our industry partners to simplify this clock, to make it much more compact and robust, and we will put it into a network center of British Telecom, a really noisy environment with lots of temperature changes, not good for precision measurement, and we will show, hopefully, that this clock will still work and operate even and can be operated even by somebody without a degree in atomic physics. The second challenge is that the typical scheme used to operate the clocks is quite complicated. We need to interrogate this ultra-narrow transition in strontium, and that is done usually by shining a laser beam on these atoms and looking for the reaction of the atoms. And it would be much nicer if the atoms could send out a laser beam directly on this clock transition. This is hard because it's such a narrow line with transition and the atoms don't scatter much light. But using tricks from the second quantum revolution, superposition states, we will hopefully be able to do just that. And we have established a nice collaboration between 6 research institutes and 6 industry partners to make this a reality. And thank you very much for your attention.
Thank you very much.